Swayam Prabha. Digital India. Educated India.
Hello everyone. Now our present topic is that behavior of card during transient state. So, what is transient state? Suppose a new card, after maintenance it is cleaned card, we start the machine card and the feed is started. So, during that period the cylinder gets loaded gradually with the each every rotation and till it reaches the equilibrium position. Similarly, that it also deliver the material to the doffer initially at the lower rate, but ultimately after certain time it gets equilibrium is reached. So, during that period, so how the cylinder is getting loaded and how the material is getting transmitted, that we will discuss here. And also the transient state reaches when we stop feeding, like we just stop feeding, still at that time the cylinder loading is there, fibers are still in the cylinder. It gradually gives the fiber, transfer the fiber to the doffer and gradually the fiber load on the cylinder reduces and gradually becomes 0, it becomes clean and the transfer of the fiber to the doffer also gradually reduces. So, this total phenomena during the transient state we will discuss first, and after reaching the equilibrium condition. So, what is the total load present in at different location of the cylinder, because cylinder is the only portion where the fibers are continuously loaded. Fibers are not loaded in the Licarin or in the dropper. Licarin takes fiber from the feed roller and 100% it gets transmitted to the cylinder, and from the doffer it takes fiber from the cylinder and transmits the fiber to the doffing system. So, doffer and cylinder we do not discuss the loading, but in cylinder we will discuss, we will calculate, we will try to see the what is the loading of the cylinder. Now, first let us discuss the transient state. So, behavior during the start of feed, that means we are trying to load the fiber initially at that stage. So, here the cylinder is there and flat and Licarin starts feeding the fiber depending on the rate of production. We have some production P rate, at that rate the fiber will be fed. So, Licarin, but in the cylinder initially it is empty, but cylinder will get loaded gradually. The feed will be as per the production rate. Now, in the first revolution of the cylinder, what happens? You can see, let the amount of fiber fed per revolution of cylinder from the Licarin to the cylinder, it is of F equal to production. So, F is the fiber we are feeding, which is equal to the production rate. and production rate is constant. So, here we feed the fiber at constant speed, and considering we are neglecting the waste percent here. So, whatever we are feeding, so we are that is the production rate. If we assume the waste percent is negligible. So, amount of fiber present to the doffer is B1. Okay. So, amount of fiber present to the cylinder from the Licarin is F or P, but amount of fiber present to the doffer by the cylinder is B1. B1 will be equal to F equal to P, because total fiber in the first cycle will be presented, because whatever fiber is coming. So, this is the cylinder, Licarin gives, suppose it is a F fiber equal to P fiber, it is coming in the at that fiber. The total fiber will be presented. We are talking about the presented, not the transmitted. Presented, this total fiber, this is B1, B1 is for the first cycle and that is P. So, total fiber is presented to the doffer. Okay. We are talking about only presented, not the transferred. Now, the amount of fiber transferred to the doffer in the first cycle, which is denoted by C1, and which is definitely lower than the B1 or P by the gamma. So, B1 multiplied by gamma is the amount of fiber transferred to the doffer, and gamma is called transfer coefficient, and gamma is less than always 1. 100% fiber will not get transmitted. So, which is equal to P gamma. Okay. Now, gamma is a transfer coefficient, and amount of fibers retained by the cylinder is B dash 1 in the first cycle. So, this is the fiber coming, P fiber is coming, doffer is taking P gamma, and remaining fiber P minus P gamma, which is B dash 1. This fiber is actually retained by the cylinder, which is there. So, retained by the cylinder is the B dash 1 in the first cycle. So, what is that? B dash 1 will be B1 presented to the doffer minus C1, which doffer takes away from the cylinder, and the remaining fiber is B1 minus C1, which is nothing but P multiplied by 1 minus gamma, and gamma is the transfer coefficient. This is the situation for the first revolution of the cylinder. Now, coming to the next revolution. In the second revolution of cylinder, what happens? In addition, the additional P is coming to the cylinder, because as the production rate is P, and the retained fiber is there P dash 1 from the first cycle. This 2 will be added and again presented to the doffer. So, the total fibers presented to the doffer will be, so what is the that is B dash is the 1 minus B dash 1 will be 1 minus gamma, that we have already seen earlier. So, this P plus B dash 1, this fiber will be presented to the doffer again. So, the amount of fiber presented to the doffer in the second cycle, second revolution of the cylinder is B 2, which is nothing but B 1 dash by plus P. So, it is P plus P multiplied by 1 minus gamma. So, this is the fiber presented to the in the doffer by at the second revolution. So, amount of fibers transferred to the doffer. So, what will be there? Whatever presented multiplied by transfer coefficient. So, B 2 is the presented multiplied by transfer coefficient, that is the P gamma plus P gamma multiplied by 1 minus gamma. So, this is the fiber transferred to the doffer. Now, how much fiber is retained up at the second revolution? That will be B 2 minus C 2. So, B 2 minus C 2 will be the fibers that we can just rearrange this, it will become 1 minus gamma square. So, just if we rearrange this equation, it will become this. Okay. Now, if we see here P, if we take common, gamma plus gamma minus gamma square. Okay. So, P 1 minus 1 plus 2 gamma minus gamma square. Okay. So, we can see here 1 minus this, and what we will do, P 1 minus what we are getting is gamma square plus 1 minus 2 gamma. So, we are getting P multiplied by 1 minus gamma square. So, that we are getting, and so by rearranging this equation we are getting this, and now the amount of fibers retained by the cylinder it at the second cycle, second revolution is B dash 2, which is nothing but B 2 minus C 2. B 2 is this one and C 2 is here, this is C 2. So, we can see the P plus this is B 2 and here it is a C 2. So, ultimately we are getting this equation by rearranging this. So, 1 P multiplied by 1 minus gamma plus P multiplied by 1 minus gamma square. So, we can see that we are getting one series, clear series we are getting in first revolution P multiplied by 1 minus gamma, and in second revolution P multiplied by 1 minus gamma plus P multiplied by 1 minus gamma square. So, we are getting one series here. So, we can predict in the third revolution. So, let us see in the third revolution what we are getting it. In addition to the P, the retained fiber B from the second revolution, that is B dash 2, will also be presented to the dopper. So, this fiber will be again presented to the doffer, and what we will be getting? So, we will just add P plus B dash 2. So, what B dash 2 we have got this from the earlier relationship, and if we get this amount fibers presented to the doffer is B 3. So, B dash 2 plus P. So, this total fiber B 3 is presented to the doffer. So, we will let us get So, this P plus this B dash 2. So, these fibers are presented. Now, the amount of fibers transferred to the doffer, which is C 3, which is nothing but B 3 multiplied by gamma. Again, if we multiply this with the gamma, we will get this equation P gamma, we are just multiplying every part with the gamma, and by rearranging what we are getting P multiplied by 1 minus gamma cube. This is the relationship we are getting at the for the third revolution. So, this fiber is transferred to the doffer. Okay. Now, what we are getting, the fibers remaining in the cylinder at the third revolution will be B 3 minus C 3. B 3 is presented and C 3 fiber is taken away. So, B 3 minus C 3 will be, this is B 3 and this one is C 3. Okay. So, that is, now we get the from the previous slide, the third revolution, the amount of fibers present to the doffer B 3, we get this. Okay. And now, for generalized equation for nth revolution, the amount of fibers presented to the doffer, that is B n. So, third revolution it is B 3. So, for nth revolution B n. Now, we can get the relationship here, B n will be P plus 1 minus gamma, P plus 1 minus gamma square. This series will continue and ultimately it will be n minus 1. So, for third cycle it is n 3 minus 1, up it goes up to 3 minus 1. So, there will be the power will be n minus 1. So, here it is a n minus 1. So, this is the generalized form for the fibers presented to the doffer at nth cycle, because that now the saturation is not reached. So, during saturation time it is there, and when the saturation is reached, that means the B n will be equal to B n minus 1. At that condition the saturation is reached. Okay. Now, that if we just if we get the, if we add, this is the in a series, this series is, if we get use this series, this we will get this value P multiplied by 1 minus gamma power n divided by gamma. So, this is the relationship we get for B n, that is amount of fiber presented during the starting after nth revolution. And from the earlier slides of third revolution, the amount of fibers transferred to the doffer. So, we are getting, this is the C 3 amount of fiber transferred to the doffer is P multiplied by 1 minus gamma cube. So, from that relationship we can calculate C n also. So, amount of fibers transferred to the doffer C n at nth revolution we will get. So, in place of 3 we can use n here. So, C n is there. So, amount of fiber presented to the doffer B n is this, okay, and amount of fiber presented. So, for nth revolution amount of fibers transferred to the doffer will be P. So, Bn multiplied by Cn. So, P multiplied by 1 minus this. Okay. So, amount of fibers presented to the doffer Bn and amount of fiber transferred to the doffer will be multiplied by gamma. This is the thing. Now, amount of fiber retained by the cylinder will be Bn minus Cn. Okay. So, amount of fibers retained by the cylinder after nth revolution, that we can see here. So, Bn minus Cn, that is B dash n will be Bn minus Cn. So, this is Bn and here is Cn, this is the relationship. So, at this condition, now we can just simplify, from rearranging this equation we get this equation, which is the P multiplied by 1 minus gamma power n multiplied by 1 by gamma minus 1. So, we just rearranging this equation, we are getting the amount of fiber retained by the cylinder. So, when do we get the steady state level? Steady state level we n, when n is very high, after certain time, after n is very high n. So, we get the steady state level. Let us assume n tends to be infinity. So, at that stage, so it will get steady state condition n equal to infinite. So, here for B infinite, that is amount of fiber presented to the doffer is B infinite, it will be B, it is equal to B P minus 1 minus gamma to the power this infinite will be there. So, ultimately we will find this becomes 1, this will be 0 because gamma is less than 1. So, that power infinite higher, it will this part will be become 0. So, ultimately this will be P by gamma. Okay. So, at that stage, so that is the fiber presented to the doffer and this is the C alpha, that means here C infinite is equal to C, that is fiber taken by the this doffer, that is fiber is transferred to the doffer will be P by gamma multiplied by gamma. Okay, that is because C is B into gamma. So, that is why it becomes P. That means, at the steady state condition whatever fiber is fed, that is transferred to the doffer. So, that is the system and this is the simplified derivation of the fiber movement from the Likarin to the doffer. Okay. And we can calculate the cylinder loading based on this understanding. So, B dash gamma will be B minus C, that is the load on the cylinder. That is B minus C, that means whatever fiber is presented. So, P by gamma is the fiber presented and P is the fiber is taken away by the doffer. So, P multiplied 1 by gamma minus 1 is the fiber retained by the cylinder at nth, at the very high infinite cycle, that is at the steady state condition. So, the input, if we see input of the cylinder revolution is there, the input is constant which is P and we can see the cylinder load cylinder load gradually increases and it is basically it reaches to a particular level. So, cylinder load in the operation layer it is a cylinder loading gradually increases. Okay. So, here from there we can get the value of the cylinder load at any stage, at any number of this cylinder revolution. So, amount of fiber transferred to the doffer Cn here. So, we can see that amount of fiber is transferred to the doffer is increasing and it is reaching the increasing with the cylinder revolution and it reaches the your this steady state condition. Okay. So, operation layer cylinder load is shown by the hatched line zone. Now, in case of opposite, what happens when we stop the feed, cylinder is loaded and it is a steady state condition, suddenly we stopped the feeding. Now, what will happen during that time? Because it is a transient state that as I have mentioned initially when we start feeding it is transient state, its loading increases, but when we stop feeding it is again transient state, but the loading cylinder loading gradually reduces. Now, let us say for first revolution again the quantity of material on cylinder is P by gamma. So, that we have seen already in steady state condition the quantity of material it is P by gamma. Initially when we discussed at the starting portion the initially cylinder load was 0, there is no load, but here at the steady state condition we have already seen. Let us go back, you can see that here this is the cylinder load which is presented to the doffer. So, that is P by gamma. So, that will actually continue here. When you stop the feeding the quantity of material on the cylinder it's B equal to P by gamma. Now, amount of fibers presented to doffer at the first revolution of after the feed is stopped is the same P by gamma. Now, the fibers which will be taken away by the doffer at the first revolution which is equal to B1 into gamma C1 which is nothing but P, and amount of fibers retained by the cylinder what will have basically it is a B1 dash B1 minus C1, this we have seen earlier. This is the first condition, first revolution after cessation. Now, the next cycle, in the next cycle what will happen? The cylinder will have this load only, because there is no additional feed. So, in earlier case we kept on adding the P value. Here there is no additional fiber because it is feed is being stopped. The for second revolution the amount of fiber presented to the doffer B2 equal to amount of retained fibers retained in the first revolution, because there is no additional feed. So, it will be remaining same. So, these are same as there is no additional feed. So, B2 and B1 dash will remain same. So, amount of fibers transferred to the doffer will be B2 multiplied by gamma. So, this is the amount of fiber is getting transferred to the doffer, that C2, and amount of fibers retained by the cylinder will, the B2 dash will be B2 minus C2. So, again B2 minus C2. So, this will be here what we are getting. So, we can just rearrange this equation, the P multiplied by 1 minus gamma square by gamma. Okay. Now, for nth revolution we can see the amount of fibers retained, by the cylinder will be 1 minus. So, for second revolution this is the thing, okay. For nth revolution, second revolution, Bn will be, this is the Bn for the next revolution. So, it will be this. So, cylinder loading, amount of fiber retained by the cylinder will be P multiplied by 1 minus gamma power n minus 1 by gamma. So, this is the generalized equation, and Cn, the term is that, what is that Cn? That is the amount of fibers transferred to the doffer will be this, and B dash n will be amount of fiber retained by the cylinder will be P multiplied by 1 minus n power n by gamma. So, which is actually, you can see these are the same. So, we can get the generalized equation for the fibers when there is no feed, or the amount of fibers and the cylinder when the feed is stopped. So, in steady state value will be B infinite will be B is 0. So, at the extreme case when there is a infinite value. So, you can see here. So, here in case of its, if it is infinite, so it will become 0, this will become 0. So, Bn will be 0, this will again become 0, Cn will be 0. Okay. So, that way, and B dash infinity. So, for if we stop the machine and if we run for long time, so load will on the cylinder will be 0, because cylinder will be totally cleaned theoretically, and then so fiber transfer will also be, there won't be any fiber transfer, this will be 0. So, that we can achieve, we can get from this equation. So, as with the increase in the number of cycle, these values keep on reducing. Okay. In case of at the starting point, the values keep on increasing, here the values keep on reducing. We can see here with the cylinder revolution at the cessation, we will see this is the production, we stopped the feeding, gradually the cylinder load reduces and finally it becomes 0. Now, what we will start, we will discuss the cylinder load at different sections. So, cylinder loading is very important, it affects the quality of the product. So, we must know what is the cylinder loading at different total loading and also at different sections. So, cylinder is actually now divided into different section. different segments we are dividing. Now, you can see here the cylinder is divided into different segments. This is the Licarin, here is the Doffer. Now, between Doffer and flat within the zone alpha 1, this is one zone, zone 1. In the carding zone between flat and cylinder, the alpha 2, that is the second zone. Between the flat and Licarin, this is the zone 3, okay. And in this zone and remaining layer of fibers are there, which is within the cylinder. So, the Q2 is the fiber layer distributed over the entire periphery of the cylinder. This Q2 is the layer, this is the Q2 is the layer of fiber which is actually total layer is it is on the entire periphery of the cylinder. So, here this Q2 is there, this will remain, that actually Q2 helps in fiber mixing, fiber blending, it is we will discuss separately. This portion cannot be clean, it should not be clean, because if the fiber the transfer efficiency is 100%, it is also not good, because transfer efficiency is a lower, transfer efficiency is good because of the fiber, it allows the fiber blending, mixing, and higher transfer efficiency, lower very low transfer efficiency will actually increase the, it is also not good because it will increase the cylinder load. So, Q2 is the fiber layer on the entire periphery. Now, Q1 is the fiber layer distributed over this Q1 is the fiber layer. So, alpha 1 and alpha 2. So, that is the, this is the layer, here it is a Q1, Q1 is the layer between alpha 1, that means it is starting from that starting of the flat zone and up to the Doffer. So, that is Q1 and it is superimposed on Q2, Q2 is at the base and superimposed on the Q2, and Q3 is the fiber layer over alpha 3, that is alpha 3 is that zone from Licarin to flat, starting of the flat. So, in this zone it is a Q3. So, we will try to measure, calculate the this 5 quantity, and Q3 is superimposed on Q2. Now, QFS is the layer of flat strip within the working zone. So, this is the QFS in this zone, working zone, whatever flat strip is there. So, flat load in the working zone of flat and distributed over alpha 2 in this zone. So, what we are trying to get, the cylinder load at different zone, and in addition to that flat is also loaded. So, from at any stage we can calculate the total fiber load in the carding machine. So, if we calculate all these parameters, and QL is the fiber layer on the Licarin. So, Licarin will have, sorry, in this Licarin, that is QL, in this zone from the feed roller to the cylinder. So, this zone will have the fiber load. Doffer we are not taking, because Doffer it's already it's getting immediately dropped. So, these are the total fiber load that we are interested in calculating. Now, one by one we will do. We will be interested in this first, this one, which is shown by the gray shading. So, the area of interest is shown by the gray shading. Weight of flat strip in the working zones, QFS, as we have. So, this we will first calculate. Let us see what happened. So, radius of cylinder is RC, it is in meter, radius of cylinder. Now, metric count of flat strip. Here what is the metric count? So, this is the in meter per gram, metric count is the actually indirect count. So, meter per gram, it is NFS, metric, that flat strip, that is the layer which we know that the whatever fiber layers are there, that hank is NFS. If we know NFS, then quantity we can calculate. So, quantity is that we know the cylinder radius and alpha 2 is the angle. So, the total length, alpha 2 is the angle not in the degree, it is in radian, okay, radian. So, alpha 2 multiplied by RC is the total length. If we know the length here and divided by the metric hank. So, this is the RC is given in meter. So, RC multiplied by alpha 2 is the total length, this total length in meter, and if we divide this by NFS, that is metric count of flat strip. So, we can calculate the total flat strip present. So, this is the total flat strip present. Here one thing is that we must know the metric count, that can be calculated. So, total flat strip is at the working zone is this. So, if the waste percent is I in flat, let us assume the what is the flat waste is I percent, and flat speed is V F in millimeter per minute, card production rate is P, that is in kg per hour, and flat strip produced per hour becomes this. What is that? P is the production rate, I is the waste percent, flat waste percent. So, divided by 100, that is in kg per hour. Okay. Production millimeter per hour it was there, and this one is 10 pi kg per hour. Okay. So, 10 its 10 pi will be in gram per hour. So, that way we can calculate the how much flat strip production. Okay. Now, weight of flat strip in working zone is QFS. So, we have seen the flat strip production is 10 pi gram per hour. So, length of flat strip produced per hour, what is the length? So, we know the flat speed, Vf is the flat speed by 60 divided by 1000. So, it should be meter per hour. Okay. So, Vf is the flat production in millimeter per hour, millimeter per minute. Okay. So, Vf, from there we can calculate the flat length of flat strip, and using equation 2 and 3, so that is hank of strip we can calculate. So, flat here earlier equation flat hank was unknown. So, from there from the flat strip, total flat strip, and if we know the flat speed, we can calculate the flat hank. So, NFS can be calculated by the VFS by 1000 pi. So, it is in milligram per meter per gram. So, meter per gram, that is the NFS. So, in this NFS we can use in the earlier equation, substituting this equation. So, we are getting this is the equation 1, and here NFS was unknown. So, NFS we can calculate from the production rate of production and speed of the flat and the flat strip. So, that we can, if we substitute this, we get the QFS value. So, QFS means the total load, flat strip load in the working zone will be, that you just substitute, we are getting 1000. RC is the radius of the cylinder, alpha C alpha, this is alpha 2 will be the zone, and Pi divided by 6 Vf. Okay. So, that way we can calculate the flat load during in the working zone. So, here the flat that metric hank was calculated from the flat strip and the production rate. Now, coming to the next session, next zone, which is the weight of fiber layer on cylinder section between flat and offer. So, in this zone, this is shown by this gray shaded zone. In this zone, what is the weight of fiber in the that zone? So, Q alpha 1. Okay. So, what is Q alpha 1? Again, that is RC multiplied by alpha 1 and N alpha 1. So, what is N alpha 1? N alpha 1 is the hank of fiber layer in that zone. So, RC length of the arc is RC alpha 1, that is this arc length, because that as similarly we have done, the alpha 1 is the angle in radian, RC is the radius of the cylinder. So, we can calculate the arc length, and let the metric hank of the layer be in the layer Q1, it is N1, and total layer. So, N1 is the layer in that zone only, and total layer. So, N1 Q1 plus Q2 layer, it includes, if we include Q2 layer which is inside throughout the cylinder zone. So, Q1 plus Q2, it will be N alpha 1. So, that is the metric count of the metric hank of this layer. Okay. And the sliver is the NS, the metric hank of layer of sliver NS meter per gram. So, weight of fiber layer in that section between flat and offer. So, we have seen Q1 is this layer Q2 in alpha 1, layer Q1 plus Q2, and sliver NS, because sliver is being formed here. Okay. Whatever now, K is the transfer efficiency. So, what happened, this N alpha 1 and N S is related with the K. That means from N alpha 1 fiber gets transferred to the Doffer to form the sliver Ns. So, this ratio N alpha 1 is the total this layer N alpha 1 divided by N 1 layer Q 1 total, that is the transfer coefficient, transfer efficiency. Okay. And N alpha 1 equal to, so we can calculate N k divided by 100, and this N alpha 1 by N 1 is less than 1, ratio of metric count. Ratio of metric count, what ratio? N alpha 1 is the, this is the N alpha 1 layer Q 1 plus Q 2, so meter per gram, and N 1 is the metric count of the only layer 1. So, this will be less than 1. So, sliver hank Ns can be written. So, what is the sliver hank? So, 3600 Vd by 100 into P. So, that is the sliver hank we can calculate from the production rate and delivery speed. Vd is the delivery speed of the Doffer, and P is the rate of production in kg per hour, and from there we can rearrange this equation. So, that we can, this is a meter per minute. So, from there we can calculate that Vd is the surface speed of Doffer, it is in meter per second. P is the production rate in kg per hour. Ns can be written as the N1 by Vd by Vc, or N1 equal to Ns into Vc by Vd. So, that way we can calculate the production rate and Ns and N1. Okay. So, weight of fiber layers on cylinder section between flat and Doffer Q1 is then, so substituting Ns from from equation 5 and using equation 6. What is equation 5? This is Ns, equation 5, and using in equation 6 here N1 we can calculate. Okay. So, N1 is equal to 3.6 by Vc by P. So, that is N1. Now, we can see here, we can go back. So, that is the N1 here, N1 is the layer Q1. So, this is the hank of layer Q1. So, we can calculate the hank of layer Q1 . So, this is the hank of layer Q1, we are getting it. So, from this equation, so substituting the hank of layer Q1 in equation 4. What is equation 4? This is the equation 4. So, N1 we are substituting here, so N1 is this. So, the N1 equal to 3.6 velocity of cylinder divided by P. So, Vc by P multiplied with this. So, from this N alpha 1, and we can that is N the Q, from here we can calculate the Q alpha 1. Q alpha 1 is becoming that 100 Rc alpha 1 P divided by 3.6 multiplied by Vc and K. So, we can see Q alpha 1 from the earlier relationship. So, this is the, these are the relationship here, and we can get Q alpha 1. So, here RC is known, VC is known, K is known, K we can calculate. So, everything is known, so we can calculate the quantity of fiber present in the zone alpha 1. Now, we will see the quantity in the cylinder flange zone. So, quantity layer fiber layer on cylinder under flat zone. So, this is the area, and we will calculate in the similar way, exactly in the similar way. So, here layer Q1 and Q2 are present on the section beside the fiber layer QFS. Okay. So, Q1 and Q2 are present, Q1 and Q2 are present beside the layer QFS. So, QFS we have already measured. So, what we are interested in? We are interested in the fiber layer on the cylinder itself. Now, only on the cylinder. So, combined hank of Q1 and Q2, it becomes N alpha 1, which is equal to N alpha 2, because this fiber is coming here in this zone. So, N alpha 2 we have already measured. So, N alpha 1 and N alpha 2 will be same, because this fibers this layer is coming to the this alpha 1 zone, same between flat and buffer zone. Okay. So, N alpha 1 we have already calculated earlier. So, N alpha 1 is the metric count between the this zone. So, which is equal to, so Q alpha 1 equal to R C alpha 2 by N alpha 1. So, R C alpha 2 is the this arc length, and arc length divided by the metric hank will give you the give us the total weight of fiber. So, this is very simple. So, we can get this is R C, we just substitute is, so R C alpha 1 and divided 100 P R C alpha 1 3.6 by V C by K. So, QFS is actually we have already calculated. This is the method where waste percent is I, flat strip is there, card production rate is P. So, this we have already calculated. Now, total weight of fibers between flat and cylinder become, so Q alpha 2 plus QFS. This if we want to calculate the total fiber weight here. So, this it will be there. So, we if we add this two, we get this relationship. It's so from there we can calculate the total fiber load in the zone alpha 2. Now, coming to the another zone alpha 3, that weight of fiber layer on the cylinder section between liquor in and flat. So, between liquor in and flat in this section, what is the total load? So, we will proceed in the exactly similar way. So, E is the liquor in waste, here the liquor in waste will be there. P is the production rate. So, we want to calculate the Q3 here. Nx is the matrix hank of the lap. What is the lap hank we are calculating? And Y is the total waste of card. Vf is the feed roller speed meter per second, and N3 is the metric hank of the layer passing from the liquor in to cylinder, that is N3. So, actual draft between the feed roller and cylinder becomes mechanical draft by 100 minus by multiplied by 100 by 100 minus waste percent So, E is the waste percent, and mechanical draft, what is mechanical draft? Cylinder's surface speed by feed roller surface speed. This is the mechanical draft. So, actual draft we can calculate if we know the waste percent. So, hank of layer Q3. So, what is the layer Q3 hank? So, metric hank of lap is known, and if we know the draft, actual draft. So, from if we multiply by and actual draft, we get the hank at the Q3. So, lap is there and hank after waste percent, whatever liquor in waste percent. So, we get the hank here Q3. So, N3 is the hank, it is in meter per gram, metric hank. Weight of fiber layer on cylinder section between this in this one, that means total weight will be there. So, at steady state production rate, feed rate multiplied by production rate will be feed rate multiplied by 1 minus y by 100 minus y by 100. So, y is the waste percent, nx is the metric hank. So, total waste percent of card. So, P production rate VFR by 100 by this is feed rate, this is the feed rate, and here is the equation. So, where feed speed Nx is the hank of the metric hank of the lap. So, from there we can calculate the production rate, and from there Nx is the metric hank, we can calculate from this, we can just rearrange this equation, metric hank of the lap, substituting Nx in equation number 9 for N3. So, N3 here we can get this. So, Nx we can substitute. So, we can get the equation number, we can see once the equation number 9, this is the equation number 9. So, we can substitute here Nx. So, Nx we are substituting. So, we get this equation. Okay. So, this is the Nx value, from there we are getting this N3. N3 is the metric hank at this zone. Okay. So, this is N3, this N3 equal to Nx multiplied with this. So, Nx is actually is getting transferred, substituted. So, thus rearranging this equation, we get N3 equal to 3.9 multiplied 3.6 multiplied by 100 minus y multiplied by Vc divided by P multiplied by 100 minus E. So, that is the hank of the metric hank of the zone N3, fiber layer N3 between liquor in flat. So, since Q alpha 3 is the weight of fiber layer in Q2, Q alpha 3 is the weight of fiber layer in Q2 and Q3. So, over the arc alpha 3, okay. So, Q2 is there. So, this is the fiber layer here, Q2 and Q3 is added. So, this will be totally added here, Q alpha 3 will be the total load on, that is this is Q3 and Q2. We have already calculated this and Q3 is calculated. So, total fiber load at this zone is derived. So, weight of fiber layer in cylinder section between Doffer and Likarin. So, between Doffer and Likarin here, that is nothing but it is a 1 minus 1 by n beta divided by 1 by n alpha 1 equal to 1 minus k by 100. K is the transfer coefficient and beta is the this zone, cylinder zone. So, n beta is metric count at the zone beta under the cylinder, which is Q2, and material in alpha 1 zone is heavier than zone beta. The alpha 1 zone, it will be heavier because the some portion of fibers are transferred to the Doffer. So, that is as the portion of fibers are transferred to the Doffer by factor k. So, it will be lowered by factor k. So, n beta we know this is the n beta n alpha 1 by multiplied by this. So, n alpha 1 zone it is, and if we take into account of the transfer coefficient. So, n beta can be calculated from n alpha 1. If we know the transfer coefficient, this is will be meter per gram. So, equation number 10, n beta we have calculated, that is everywhere we have seen, we are actually observing we must calculate the metric count first, then we can calculate the load easily by the arc length. So, n beta is calculated. So, we can calculate the load. So, this is the n alpha 1 here. So, n alpha 1 is given. So, from equation 8 and 10, 10 is the equation n beta here. So, 8 and 10 we can calculate the n beta from this n beta is there, and then we can calculate the quantity of fiber in beta, which is the arc length RC into beta divided by n beta, which is the metric hang. This gives the in gram what is the weight of fiber. So, what we have done, we have calculated, we have seen, we have calculated the total weight at different zones of fiber. So, we can now calculate that if we add everything, we will get the total load on carding zone. So, QB is if we replace this in beta, so we will get the quantity of fiber in zone beta. So, it is defined as the percentage. So, transfer efficiency, what is transfer efficiency? It is defined as the percentage of fiber transferred to the Doffer from cylinder per revolution of the cylinder, and mathematically what we can do, we can get K is equal to Q by Q multiplied by 100. Q is the number of amount of fiber transferred to the Doffer per revolution of the cylinder, K is the transfer efficiency, and Q is the load on cylinder, that is quantity of fiber in the on the cylinder in the steady state condition. So, on the cylinder we can calculate the fiber in the steady state condition, and amount of fiber transferred to the Doffer per cylinder revolution we can calculate, and from there we can calculate the transfer efficiency. So, it is defined as the percent of fiber transferred to the Doffer from cylinder per revolution of cylinder. So, that during one revolution of cylinder, the length of sliver delivered by Doffer is basically one cylinder revolution. We can see that 2 pi r d is the Doffer circumference, okay, 2 pi r d, and Nd is the Doffer RPM divided by Nc. So, per revolution of cylinder, this much length of sliver is being fed, delivered, okay, by the Doffer. So, Doffer speed, Doffer RPM, and Nc is the cylinder. Doffer RPM is much less than the cylinder RPM, that we know. So, amount of fiber transferred to the Doffer per revolution. So, what we have calculated earlier, Doffer from the amount of fiber. So, one revolution, the length of fiber transferred to the Doffer, okay, delivered by the Doffer. So, that amount of fiber is actually transferred. So, per revolution of fiber cylinder, its Q can be calculated from the L. L is the amount of the length of the sliver. So, if we know the sliver hank, so sliver hank in any, if we know and length is known, from there we can calculate the total quantity here. So, here you will see this is coming to be this 36, the factor comes from the, it is just, it is actually conversion from the inch and yard, and 453.6 is the conversion from the pound and gram, 840 yards. So, from there we get all this equation. So, L is being replaced here by this values which we have already derived. So, hence the K value we can calculate. So, K value is nothing but Q by Q. Q is the total load. So, total load we know we have calculated. So, Q is known here. Q is the amount of fiber transferred per revolution divided by total load. Total load is Q on the cylinder and multiplied by 100, that is the transfer coefficient. So, we can calculate the transfer coefficient also. So, if P is the production rate in gram per minute, so production rate, then the P will be, P is the production rate in gram per minute. So, P can be calculated from the hank of the sliver. Sliver hank, we can calculate the P by knowing the Doffer radius and Doffer RPM, that is the production can be calculated, and then transfer coefficient we know it is the Q by Q, and production is in gram here, and hence K can be expressed as P production by N C into Q. So, where NC Vc is the surface speed of cylinder and NC is the Vc by 2 pi Rc. So, from there we can calculate K is equal to 2 pi Rc multiplied by P by, so from this equation, from equation 6 we get by Vc into Q. So, K can be expressed as P by Nc into Q. So, surface speed of cylinder equal to 2 pi Rc multiplied by Nc, where Nc is the cylinder RPM and Q is there and Rc is the radius of cylinder. Okay. So, from there we can calculate K is transfer efficiency is calculated, 2 pi RC P is the production divided by Vc into Q by 100. So, that is the transfer coefficient. So, transfer coefficient is related with the mass of fiber transferred transferred to the doffer per revolution of cylinder. The transfer efficiency can be easily calculated from equation number 4 or 7 after experimentally determining the magnitude of carding load. So, carding load, if we can calculate Q, total carding load if we can calculate, so we can actually get the transfer efficiency. So, in experiment, in the laboratory experiment, we do calculate, but first we cannot, we do not calculate theoretically, but we calculate the cylinder load experimentally, and then from there we can calculate the transfer efficiency. And that is all about this section. So, we will stop here. Thank you. In next session we will start with a new topic. Till then, thank you.